Good afternoon, everyone, and thank you for joining us for today's webinar. We are going to get started here in just a few minutes, but before we do, I would like to go over a few housekeeping items with those of you that have joined us in the meeting. For those of you that we do have in the meeting, the first thing I would like to make mention of is our chat pod, which is located on the left-hand side of your screen marked chat. This chat pod is the best way to communicate with us should you experience any technical issues. Also, if you would like to ask any questions of our presenter, please make sure that you do utilize that chat pod, and we will hold those questions and then get them answered of our subject matter expert at the very end of today's webinar. If you do happen to experience any technical issues, again, please make sure that you do let us know in the chat pod, and either myself or one of our customer service representatives will make sure to get you taken care of. I apologize for that. Again, if you do experience any technical issues and you find that the chat pod is not working properly, or you would like to utilize our toll-free number as well as our email address, you will find those directly above the live feed window. We have also put a special note in today's event. Google Chrome recently did an update, which we are working with them to navigate through. But if you happen to be using Google Chrome, we do suggest that for today's event you do utilize Mozilla Firefox if you have that available. If not, then there is a direct link to the live feed that is directly above the live feed window. You can click on that. It will open up a new web browser for you, and that will give you access to today's webinar. Also below the live feed window, we do have our closed captions that are currently running, and they will be running throughout the entirety of today's event. So if you would like to follow along there, please feel free to do so. We do have a couple minutes before we get started. We do like to find out a little bit more about our audience before we do start our webinar. So if you could take a few moments and type in your location there in the chat pod, that'll give us some fantastic feedback about our audience and where everyone is joining us from today. Again, we've got a minute or two before we get started. I'll probably come on once more to go through housekeeping with those that do come into the room over the next minute or two, and then we'll get started shortly. Thank you for joining us today. Good afternoon, everyone, and thank you for joining us for today's webinar. We are going to get started here in just a moment, but before we do, I would like to go over a few housekeeping items with those of you that have come into the room. The first thing I would like to make mention of is our chat pod, which is located on the left-hand side of your screen marked chat. This chat pod is the best way to communicate with us should you have any questions regarding today's material. All questions pertaining to the material will be retained until the Q&A session that will be held at the very end of today's webinar. So please feel free at any point of today's talk to go ahead and type in your questions there in the chat pod, and we will pull them out and hold them for you and make sure that they are answered during our Q&A session. Also, if you experience any technical issues, this chat pod is the best way to communicate those with us. If you do have any technical issues, just let us know there, and either myself or one of our customer service representatives will make sure to get you taken care of. Also, all of today's audio should be streaming through your computer speakers. Again, if you do experience any technical issues, you can let us know there in the chat. Also, you will look if you look above the live feed window, you will see our toll-free number as well as our email address that you can contact us directly there as well if you do have any technical issues. We have put a special note in the note section above the live feed window for today's event. If you are using the most updated version of Google Chrome, we have run into some issues that we are currently working through, but you are more than welcome to use the direct link that is on the very bottom of the note section that will take you to a direct feed of today's live event. If you're using Mozilla Firefox, you should not need to utilize that link, but if for any reason you are having problems with your player today, that direct link is going to be the best way to view today's live webinar. You will also notice as well the closed captions are directly below the live feed window, and they will be running throughout today's event. If you would like to follow along there, please feel free to do so. It is the top of the hour. I'm going to go ahead and mute my line back. I'll switch some things on my end, and then we will get started momentarily. Thank you for joining us today. Good afternoon, everyone, and thank you for joining us for today's webinar. My name is Josh Vickers, and I am with RTI International's Forensic Technology Center of Excellence. Today's webinar is entitled Up-and-Coming Separation and Detection Techniques for the Analysis of Emerging Drugs. Our subject matter expert and presenter today is Dr. Ira Lurie. He is a professor at George Washington University. He received his bachelor's in chemistry from Queens College, his master's of science in chemistry from Rutgers University, and then his PhD in chemistry from the University of Amsterdam. Dr. Lurie served almost 40 years as both a forensic chemist and senior research chemist with the Drug Enforcement Administration, where he last served as the agency's expert in liquid phase separations. He is the author of over 70 publications, including several book chapters and co-edited book entitled HPLC in Forensic Chemistry. Professor Lurie is the winner of the 2015 Paul Kirk Award, the highest form of recognition one can receive from the criminalistics section of the American Academy of Forensic Sciences. Just our quick disclaimer, the opinions, findings, and conclusions or recommendations expressed in this presentation are those of the presenter and do not necessarily reflect those of the Department of Justice. Any products and manufacturers discussed are presented for informational purposes only and do not constitute product approval or endorsement by the U.S. Department of Justice. And now, without any further ado, I would like to hand the microphone and platform over to our speaker and presenter today, Dr. Ira Lurie. Dr. Lurie? Dr. Lurie, you might be on mute.
Yes.
There you are.
Good afternoon, ladies and gentlemen, and thank you for joining me for today's webinar. Today we're going to be talking about novel techniques that one can use to analyze emerging drugs. And as most of you know, emerging drugs are drugs that synthesize to mask the fact that they are no longer controlled and an attempt to circumvent existing drug laws, and also to mask detection in standard drug tests. One of the classes of emerging drugs that we'll talk about this afternoon is synthetic cannabinoids. Well, these drugs are functionally similar to delta-9 THC, the active ingredient in cannabis, and they bind to the same cannabinoid receptors as delta-9 THC in the brain. However, while a few of them are structurally similar to delta-9 THC, for example, HU210 and CP47497, most of them are not structurally similar. And here's some examples of some synthetic cannabinoids. Of particular interest is the analysis of both positional isomers and diastereomers, because these are by far the most difficult type of compounds to analyze in a given class of emerging drugs. And here we show an example of JWH018 and 9 positional isomers. Several of the synthetic cannabinoids are also diastereomers. For example, you have HU210 and HU211, and you have CP47497 and its 3-epi diastereomer, and you can have a C8, a homolog of that compound, and also its diastereomer. Next, we're going to look at synthetic cathinones, and these are drugs that originally arrived from the drug cathinone, which is the stimulant found in the cot plant. And they have effects on the body that are similar to stimulants such as amphetamines and cocaine. Here's an example of some synthetic cathinones. And although cathinone is a primary amine, in the case of synthetic cathinones, you have, for example, methcathinone, which is a secondary amine, and you have alpha PBP, which is a tertiary amine. You also have to deal with positional isomers, and here is an example of pentedrone and 7 positional isomers. We all know about the fentanyl epidemic, and although it has leveled off in 2018, it's still rising in 2019. We also have various analogs of fentanyl, and here's an example of certain analogs of fentanyl. Again, we're concerned with positional isomers, and here is an example of 6 positional isomers of mass 350. The last class of emerging drugs that we'll be talking about today is substituted phenethylamines. And these are formed by replacing hydrogens on the backbone of a core phenethylamine with different R groups. And most of you, I'm sure, are familiar with the book Perkel, A Chemical Love Story, which deals with certain compounds such as the 2Cs that were introduced by Shogun. Here's an example of some substituted phenethylamines, which are, for the most part, primary amines. We also have to worry about positional isomers. And here is an example of 5 positional isomers of dimethylamphetamine. Now, how do we analyze these emerging drugs? And for the most part, since we're dealing with mixtures, we would utilize a instrumental approach that uses a tandem separation and a detection. What we want as forensic chemists is to get the most out of both techniques. In other words, the highest specificity. So the main theme of today's webinar is to look at some new and emerging and novel technologies that one can use to either increase the specificity of retention or the specificity of detection. I'm sure most of you are familiar with SWIG drug, which is minimum requirements for siege drug analysis, where we have category A, which is the most specific, category B, intermediate specificity, and category E, which is the lowest specificity. And it specifies that if you use a category A technique, you can use a B or a C, or if A is not available, or if you choose not to use a category A text, you can use two category Bs and a C, for example. Today, we're going to deal with the two category tests, including supercritical fluid chromatography, which just last September was added to as a category B. And we'll also look at some novel approaches to liquid chromatography. First, let's look at ultra-high performance supercritical fluid chromatography. This is supercritical fluid chromatography using less than 3 micron particle columns or equivalent. And you can see a phase diagram on the upper right, left for supercritical fluids. And it says that above a critical temperature of 300 degrees Kelvin and 100 bar, you get a supercritical fluid, which has unique properties. It has density intermediate between gases and liquid, so it has nice solvating properties, which leads to the mobile phase having intermediate selectivity between gases and liquids. It also has viscosity intermediate between gases and liquids, which leads to intermediate diffusivity, which leads to faster analysis of your chromatographic separation versus LC, but not as fast as GC. This test is performed by the base solvent being carbon dioxide in the supercritical or subcritical state. You add an organic modifier, typical methanol, and depending if you're running charged compounds, you may add an acidic or basic additive. In the lower right corner, you can see a schematic of a supercritical fluid instrument where you start with your CO2 supply. It has a gas headspace. You cool it down. You have another pump for your co-solvent. And we can run, in our instance, we're going to be running a PDA for UV detection in series with a mass spec single quad detector. And since electrospray positive does not like carbon dioxide mobile phases, we have a makeup solvent, which either is acidic or base, which will allow us to carry out positive electrospray. So why use UHP FSC? It has comparable limits of detection and repeatability and robustness of that of UHPLC, but it has up to 4 times the separation speed. It provides for a normal phase type of separation that's considerably greener because you're replacing a base solvent such as hexane, cyclohexane, and use of a modifier solvent such as methylene chloride and chloroform, with a large amount of carbon dioxide. What particularly intrigued us for the use of UHP-FSC was that back in the 70s, normal phase LC was touted for the separation of positional isomers. So UHP-FSC, being a normal phase separation, should allow a good separation of positional isomers. When you perform supercritical fluid chromatography, they have developed stationary phases that are unique for this separation mode. And the ones that we have used are ones such as 2-picolamine, diethylamine, high-density diol, and 1-amino anthracene. And you can see these unique phases in this slide. They also came up with sub-3 micron stationary phases, and for chiral separation, and the ones that we investigated are the AM1, the CL1, and the CL2. These ligands on the right are used to attract our solutes to the stationary phase, while the enantiomeric selectivity comes from these anti-enantiomeric sugars that are present. Here you see a separation of 22 synthetic cannabinoids of different subgroups using UV detection at 215 in series with single quad mass spec detection. And you can see that out of 22, we resolved with a resolution equal to greater than 11. How does this compare with other commonly encountered separation techniques? If we run GCMS, this is a total ion chromatogram for the same solutes, we can resolve 17 out of 23. If we look at UHPLC, both using a superficially porous C18, a superficially porous phenyl, or a superficially porous PFP, the most we can do is 15 out of 23. What's interesting is that even though GC has significantly higher peak capacity, that is the ability to set the number of compounds you can separate in a given chromatographic run, than LC, the overall resolution is similar because of the fact that the mobile phase contributes greatly to the selectivity, while in GC, the gas really only helps in the separation efficiency and does little for our separation selectivity. Now we see what is the main reason that we'd want to use supercritical fluid chromatography. We were able to resolve all 10 positional isomers using this technique. This compares with resolving only 4 out of 10 using GC, and at best 3 out of 10 using UHPLC. What's interesting, besides the fact of the high resolving power of this technique, is that we used a chiral column to accomplish this. We used a chiral column because back in the days when I did extensive work with capillary electrophoresis with chiral selectors, I found that adding a chiral selector to the run buffer in capillary electrophoresis also greatly enhances the separation of very similar compounds. What about the separation of diastereomers? Here we look at the separation of HU211 and HU210 using a chiral FSC column. These compounds are very difficult to separate by both GC and liquid chromatography. Here we see the separation of not only diastereomers, in this case 4, but the enantiomers of each of the diastereomers. Why? Because we're running also a chiral separation. Now, when you're doing forensic analysis, for example, if you don't have a category A test, Swig Drug says you can use 2 category B tests, and you can use 2 separation techniques that are uncorrelated. So if we look at PCA, we can see that GC, LC, and FSC are well separated, therefore showing the orthogonality of all these 3 separation tests. Even if you are performing a category A test, it is a good practice, just so you don't mix up samples, showing you didn't mix up samples, to run an additional method. What about some figures of merit for supercritical fluid chromatography? Essentially, at high, low, and medium concentrations, we get excellent percent RSDs of retention time, and we also get good RSDs for UV and mass spec. In general, UV will give you higher repeatability than mass spec. What about for quantitation? Here we show that we can get high linear R-squared values, and the R-squared values are at least over, especially for UV, 1 order of magnitude. And we also found, not surprisingly, that we get higher R-squared values using UV versus mass spec. Let's switch gears and look at a novel way of using liquid chromatography. And for this purpose, let's look at the use of type C silica for the analysis of emerging drugs, particularly positional isomers. In ordinary silica, we have cyanyl groups. Professor Petrek has synthesized silica hydride groups by converting the OH with silane chemistry to SiH. So what will happen if you run a normal silica column in the mode that's called hydrophilic interaction chromatography, which essentially is running high acetonitrile, typically around 95%, with approximately 5% water, and typically we run around 5 millimolar ammonium formate, you get a water layer on the surface. With straight silica C, the silica hydride, no such water layer is observed under high organic conditions. The consequence of this is that it takes up to an hour to equilibrate many times when you're running hydrophilic interaction chromatography. Under the same conditions, which they call aqueous normal phase, you get much shorter equilibration times. Now, the use of the silica C or silica hydride stationary phases can be very useful for forensic drug analysis. It allows us to perform what we have coined flip-flop chromatography, which works as follows. You can take your solvent reservoir on your LC, whether you have a binary or quaternary mixture, and you can fill them with your appropriate solvents. On the same silica C column, you can first run reverse phase chromatography, and then with the same solvents, but a different mixture, you can run aqueous normal phase chromatography. So the hope is, but by doing this, you get highly uncorrelated separations. We previously mentioned that you have much quicker equilibration times using aqueous normal phase with silica C than hydrophilic interaction chromatography. And it's been found that, as I mentioned earlier, that normal phase separations can be good for positional isomers, and aqueous normal phase is a form of normal phase chromatography. Here we look at various stationary phases that we have used to investigate the separation of emerging drugs, particularly positional isomers. And you can see a C18 group, a phenylhydrate, a cholesterol group, a straight silica C, a diamond hydride, which has 2% carbon impregnated on the surface. And if you run a classical silica separation using your garden variety C18, and you plot the retention factor K versus percent organic, you get the expected behavior where K decreases with percent organic. Well, if you take a silica Hillock column and you run at high organic, you increase the amount of organic, you get the opposite effect. K increases with percent organic. However, if you take a classical silica column, and when we originally introduced the term flip-flop chromatography, we performed this separation with a PFP stationary phase. Most classical reverse phase columns do not undergo this U-shaped behavior, where K first decreases and then K increases. One of the few classical silica columns that will undergo this will be the PFP phase. However, the bidentate C18 underwent this U-shaped behavior. So did the phenylhydride. So did the cholesterol. So did diamond hydride. And so did silica C. So in other words, you have in your arsenal any silica hydride column you use will undergo this U-shaped behavior. So you have a way of enhancing your separations by taking the best column or columns according to your situation. Now, I mentioned earlier that in order to increase your specificity of analysis, you can run you can run GC versus LC, GC versus FSC, for example, but you could also run reverse phase versus helix. But normally this requires the use of two separate columns. And here is an example that if we run reverse phase, G and F do not separate, but if we run helix, they now separate. So the combination of both will resolve all 8 positional isomers of pentadrone. If we perform the same experiment on a PFP column, it doesn't work as well. Only 2 out of 8 were resolved, even though the column was reversible. However, we found for a silica C column that whatever doesn't separate by reverse phase will separate by aqueous normal, so the combination of both resolved all 8 positional isomers of pentadrone. The question now is, how orthogonal are the separations using silica hydride phases? For the separation I just showed you, if we plot the relative retention time of these 8 positional isomers versus the relative retention time in reverse phase versus aqueous normal, we get an R-squared value of almost 0. Highly orthogonal. In this slide, we show PCA for the experiments that we performed, including classical C18 and helix, PFP, and the use of silica hydride. And you can see from this slide, based on Euclidean distances, that you get good orthogonality between the most of the silica C phases. In this slide, we show that if we go from a classical C18 column, run 5 separations, excellent repeatability, we then place a helix column on our system, and we run 5 injections to get terrible repeatability. That's because it took us an hour. We only calibrated in between these mechanisms for 20 minutes, and it takes approximately an hour to calibrate our helix system. If we run our silica C columns under flip-flop conditions, where we run 5 injections in reverse phase, calibrate for 20 minutes, and then run aqueous normal phase, we get extra repeatability on both. My thought would be that you could probably calibrate less than 20 minutes between reverse phase and aqueous normal. What we just showed you is either running 2 columns under different separation mechanisms or running the same column under different separation mechanisms. What would happen if you took 2 columns with different stationary phases with the same mobile phase conditions and put them in series? Supercritical fluid chromatography, which has lower viscosity than LC and therefore lower back pressures, is highly amenable to running columns in series. And we found by taking a combination of a diol and 2-pick column, we could resolve all 8. If we ran these separations alone in either diol or 2-pick, we were not able to resolve all 8. Another approach one could use to increase your specificity of your separations is to use multi-dimensional ultra-high performance liquid chromatography. Well, it's well known that if you have a single column and then you perform multidimensional separations, that the peak capacity is the product, not the sum of both peak capacities. But our approach is we are not going to run what's known as comprehensive multidimensional. We're going to run hard cutting because we're normally just interested in only the controlled substances and improving the separation of those compounds. So we're going to target which peaks we're going to send to the second dimension. But that use of multidimensional UHPLC depends on how well we use that separation space, and we'll call that fractional coverage term in our equation. We can further write an equation where we take into account that separation space, the efficient use of separation space. In other words, the more uncorrelated your two separations are in multidimensional, the more you're going to cover the separation space. So in other words, if the two techniques had R squared approximately near 1, these would exist on a straight line and all this area up here would not be used. As this approaches 0, this is going to be more scattered throughout this whole separation space. Well, we're reflecting that by using the noise selectivity factor, which is defined as 1 minus R squared. And we also are defining our peak capacity as the time end of the last peak, time end of the first peak, divided by the average width at 0.67 base. What's important here is what we call the gain factor. If we run a single dimension separation, you have a finite peak capacity, and there's only a certain amount of place in separation space you can put your peaks. In other words, you have the potential for unique retention times is limited. When you significantly increase your peak capacity, overall peak capacity by running a multi-dimensional separations, you have the possibility of more unique retention times. So what we're interested in is the gain factor. For example, for synthetic cannabinoids, if we ran a C8 column in the reverse phase mode and a PFP column as our second column in reverse phase, we gained a factor of 49, which means the likelihood of two compounds having the same retention time decreased by a factor of 40, almost 50. For the JWH positional isomers under the same experimental conditions, we have a gain factor of 10. For our pentendrome positional isomers, which I showed you previously, we have a gain factor also about an order of magnitude. This is our experimental setup where we have 3 pumps, a quaternary and a binary solvent system. We make an injection. We do its first separation on a reverse phase C8 column. In the case of our relatively neutral synthetic cannabinoids, we run reverse phase. And our second dimension for our charge compounds is hydrophilic interaction chromatography. We use a 150 microliter loop to trap our samples, The problem becomes is that the solvent strength of these trapped fractions are too strong for either reverse phase or Hillock. So we use an intermediate trapping column. In the case of reverse phase, a C8. In the case of Hillock, a Hillock trapping column of 10 micron particles. And we pump in a solvent modifier to make our fractions compatible with both either reverse phase or Hillock. And then we run a separation to elute our solutes off the trapping column into our second dimension. Let me show you an example. For the positional isomers of JWH18, we have extensive overlap. If we hard cut I2 and I4 and send it into a second dimension on a PFP column, now I2 and I4 are well separated. Let's look at an overall separation of synthetic caphenones. Peaks D2, F, and D1 do not separate. If we hard cut this peak, send it to a PFP column, run it under hydrophilic interaction chromatography, we have now resolved D2, D1, and F. We just talked about how we can improve the overall selectivity using different separation approaches. Let's go back to our category A and see what we can do to increase our specificity on the detection end. If you run classical GC-MS with electron ionization, and here are 3 positional isomers, 2,3-dimethyl methcaphanone, 3,4-dimethylcaphanone, and 2,4-dimethylcaphanone, differing on the position of the benzene ring. Their mass specs are virtually indistinguishable. If you look at additional isomers of 191, where you have differences in the aliphatic part of the molecule, in this case, the mass specs also are similar. Another limitation for these compounds is the lack of molecular ion. Let's look at fentanyl. Let's look in particular cyclopropyl fentanyl versus chronyl fentanyl. Their mass specs are virtually identical, and there is a lack of molecular ion. So our approach was to use cold electron ionization in order to generate enhanced molecular ions. And it works by taking our GC effluent through a small nozzle where it undergoes supersonic expansion, which cools our solute so that when we ionize it with 70 electron volts, we will hopefully inhibit further ionization. So here is an example of running classical EI versus cold EI. No discernible molecular ion, a significant enhancement in molecular ion. No discernible molecular ion, significant enhancement in molecular ion. What's also interesting is that the major ions are still present after cold EI, So you could conduct NIST library searches to see if you possibly have your compound of interest present. It also enhances the higher masses so that which are more informative. Let's next look, however, when we run ColdEI, even though we were able to get enhanced molecular ions, the mass specs of the problematic positional isomers were still very similar. So one possible solution is to use molecular spectroscopy. And in classical UV, where you're looking at, in the liquid phase, where you're looking at 205 nanometers typically and above, you're looking at mainly pi to pi star transitions, and we're talking about aromatics. There are N to pi star, but these have lower extinction coefficients significantly than that of the pi to pi star. Now, in order to look at alkanes, or the aliphatic part of the molecule, which are sigma to sigma star, which are in the area of 100 to 200, these are the higher energy transitions. You can use a technique called vacuum ultraviolet detection, which has been recently commercialized by VUV Analytics, which allows you now to look at UVs in the gas phase using gas chromatography. Here is the UV spectra of the 191 positional isomers, which I described earlier. And let's look at number 4, number 6, and number 8. These are compounds that gave virtually identical mass specs, but the UVs are vastly different. However, if we look at 5 and 7, which gave also very similar mass specs, their UVs are the same. However, we can use vacuum ultraviolet spectroscopy and see if we can distinguish compounds 5 and 7, because vacuum ultraviolet spectroscopy will allow us to look at sigma to sigma star transitions. And our experimental setup is we take a commercial GC, we interface it with our vacuum UV detector from VUV Analytics, and we can get a UV spectra. Since our carrier gas, in the case we're using helium, is virtually invisible to our VUV range in between 110 and 200, we can look at sigma to sigma star, and we can look at high energy pi to pi star transitions. For anyone who has performed LC, knows that their peak response for benzene-containing compounds goes up at 210, but actually the peak maximum is around 180, which you can't see in the liquid phase. So now, if we look at the vacuum UV spectra of the synthetic hafenone positional isomers, now compounds 5 and 7 will have discernible UVs. In other words, we can now distinguish not only when we have differences in the separation on the benzene ring, but differences in the aliphatic portion of the molecule can also be distinguished. So our next step is combine GC, cold-DI-MS, and VUV all in one instrument. And we accomplished using a T and few silica capillary guard columns. Here shows the separation of 24 fentanyl analogs using simultaneous cold-DI-MS and VUV detection. There is a small loss in resolution in VUV versus cold-DI due to the fact that part of the tubing in our interface is wider than cold-DI because the cold-DI is pulling a vacuum, and we have to compensate for that effect. Out of 24 analogs that we looked at, 23 exhibited enhanced molecular ions using cold-DI. So here we can see classical EI for cyclopropyl and cold-DI. And now we can see a molecular ion at 348 for this compound. Same thing for cronophenol. No discernible molecular ion by mass spec, but you can see now a molecular ion by cold-DI. However, you can see the mass specs are the same, still with cold-DI. However, if we look at the VUV, which we simultaneously obtain, the UVs are vastly different. The next question is, how specific the degree of specificity and the repeatability of the UV spectra. So what we did is we took all our fentanyl analogs that we analyzed, we added to a library that had hundreds of other compounds of different chemical industries, including the seized drugs, and we did 5 runs on a given day, and we repeated that experiment for 6 days over a 2-week period. And what we found is that the first hit, if we search for cyclopropyl fentanyl peak, the first peak that we got was, the first hit was always cyclopropyl with high determination coefficients. Cronophenol gave us the following return on our library search. If we search cyclopropyl versus library, cyclopropyl, for example, would give us 4 nines, and cronophenol would come up with a lower hit with points around 0.9685. Let's look at the case of isobutylfentanyl versus butylfentanyl. No molecular ion for both using classical, but we did get a discernible molecular ion using cold-DI. However, here, the UVs are only slightly different. So how reliable is this determination? So again, we followed the same experiment that we did for crotonal and cyclopropyl, and invariably, during these experiments, isobutylfentanyl, for our isobutylfentanyl peak, it was always the first hit. And butylfentanyl was normally the second hit with a lower coefficient, determination coefficient. Now, many people in forensic drug analysis use flame ionization detection. Some use it for drug screening, and many use it for quantitation with your gas chromatograph. Now, this is taken from the McShane firm website, defense attorneys, and what they say is if anybody uses GC FID with a single column essentially go at it, go after them. Why? Because although you get a retention time using GCFID, you're running blind. You do not know what's under the peak. However, if you use UV or VUV detection, or VUV detection in the case of GC, you do know what's under the peak because you get a UV spectra, or VUV spectra to be precise. And the question then becomes, how does it perform for quantitation? Because we know one of the major attributes of FID is high repeatability, decent limits of detection, and good linearity ranges, and good determination coefficients. And here you can see that we get at least we get approaching 2 orders of magnitude for linearity, R-squared values that are excellent, and limits of detection in the ppb range, high ppb range. Also, you can see in this slide that we get decent limits of detection also in the high ppb range for our fentanyl compounds by co-DI-MS. Here shows the great utility of our interface. In a single injection, we can get a retention time, we can get a co-DI-MS spectra, which gives us a molecular ion. We get a VUV spectra, which is highly complementary to our co-DI-MS, and we can quantitate with a high degree of reliability. The same approach, where we ran simultaneously GC, VUV, co-DI-MS, was applied to the separation of 40 phenethylamine analogs. And this shows you the GC separation. We all know in drug analysis that many times phenethylamine can be bad actors by gas chromatography. Either you can derivatize and or do a basic extract. We use a trick that we previously published where we add methanol, a sample, and sodium bicarb, and we can get good performance. Out of 40 phenethylamine analogs that we analyzed, 37 exhibited enhanced molecular ions, and this shows an example for 3,4-DMMA. And one of the nice features of VUV detection is that here we see the overlap of 2 compounds, 2,4-DMA and 3,4-DMA. Well, based on the library entries, the software allows you to actually deconvolute these peaks into 2 separate peaks, and based on their spectra. Even though they're very similar, you can actually get single peaks for each of these overlapping compounds. Here, we look at 5 positional isomers of dimethylamphetamine. If we run co-DI-MS, we see 2 things. We see not so good repeatability on 5 determinations, and we see significant overlap between these different positional isomers by mass spec. By VUV, not only do we see excellent repeatability, but we see significant differences in Euclidean space between these 5 positional isomers. Finally, we're going to talk about recent work that we've been doing on use of portable capillary LC. This instrument weighs only 17 pounds. It works on a rechargeable battery that can last 10 hours. You can connect to software by either an Ethernet cable or Wi-Fi connectivity. And we're using 150 micron internal diameter capillary columns filled with either 1.7 to 3 micron fused silica particles. You can run smaller samples and considerably smaller solvent volumes with significantly less waste, so it's a very green technique. So you're using as little as 1/50th, 500th the solvent you would use for regular LC. Now, the way you have your normal sampling valve, but the way you can keep the weight down is they use 2 syringe pumps, which you can't see here, which are very lightweight. You have a capillary cartridge that you slide in, and on it you run on-column detection using a 255 LED UV detector and a 275 LED UV detector. Our approach was to use 2 different capillary columns in series. You can't see the second one, it's really under the cartridge. And the idea is to have 2 separate capillary stationary phase that have different packing materials that will hopefully give you uncorrelated separations. The idea of this work, we go back to the work of Baker in Journal of Chromatography in 1979, where he took 78 drugs and found that at a single wavelength and just based on retention time, he could only distinguish 9% of these drugs. He found, though, if he took UV detection at 254 and 275, 95% of these drugs could be identified by their peak area ratios. Here's an example where we employed a C8 capillary, 10 centimeters, at 255 in series with a biphenyl at 275, and you can see the separation on both in on-column detection, and shows you have decent repeatability of 5 injections running a gradient. We found that for 16 target synthetic caphenones, if we look at relative retention time on the first column, we look at relative retention time on the second column, the biphenyl, and the peak area ratios, which are proportional to the extinction coefficient at both wavelengths. And we have a 2, and we ran 5 injections of each, and it determined 2 sigma. We can uniquely identify all 16 synthetic caphenones. Some figures of merit. We can get low ppm, limited detection. Our linearity range is at least an order of magnitude, and we can get decent R-squared values. One of our goals in performing this portable LC is that if you do not have a category A technique available, you could run 2 capillaries in series, which gives you 2 category B tests, and the ratio of your UV wavelengths could be a category C test. So possibly it could help a developing country that, for example, cannot afford a category A test. In closing, I want to acknowledge NIJ for funding our UHFSC project, for funding our multidimensional LC project, and also for funding our simultaneously co-DI MS VUV project. And I also want to acknowledge Elmer for funding our original work on the separation of synthetic cannabinoids and cathones using GC and UHPLC with time of flight detection. We are very grateful for Waters for the loan of our UHFSC and multidimensional LC instrumentation, and also for our initial VUV work for Elmer for loaning a gas chromatograph. All our work cannot be possible without our collaborators. I want to thank and also our students, of course, who have spent many hours performing the experiments that you've seen today. And I want to thank you for your attention, and please, everybody, be safe. Thank you.
Thank you so much, Dr. Lurie. We are going to give everyone just a couple of more minutes to type in any questions that they might have for you. While we're waiting on those questions to come in, I do want to make mention that we have recorded today's event, and we will be turning it around into our archival version over the next few days so that you may refer back to it or pass along to any colleagues that might have missed today's live event. Also, Dr. Lurie was generous enough to provide a PDF version of today's slide deck for you, our users, to be able to download. You'll find that back on the main event page where you entered today's webinar. So please make sure to get that download before you do leave today. We don't have any questions right now, Dr. Lurie, and we are a little bit over time, so I'm just going to pass the microphone back to you just for some closing words, and then we'll finish out our webinar for today.
Okay, again, I want to thank everybody for attending, and if you have any questions or want to discuss my work further, you can see my email address.
All right. We do have one question that came in, Dr. Lurie, for you, asking, could you comment on the reproducibility of the fragmentation of cathinomes with cold ionization compared to the reproducibility of 70 eV mass spec spectra?
Very good question. I don't, to be honest, I don't know the answer to that. We did not perform that experimentation.
All right, no worries at all. With that, Dr. Lurie, we are going to go ahead and close out today's webinar. Obviously, we would like to thank you for being our presenter and subject matter expert today and taking time out of your day to deliver your presentation. So thank you very much for that. We greatly appreciate it.
Thank you.
We would also like to thank all of our attendees for joining us today. These webinars are simply not possible without your attendance and support. So thank you for taking time out of your day to join us for today's webinar. We always ask that you do participate in our short survey. You will find that on the bottom right, directly below the closed captions. Simply click on the word survey. That will open up a new window for you, and you can run through the questions pretty quickly. We always use your feedback to make sure that we're providing the best webinar experience for your audience, as well as adjust any content or the way that we disseminate that information out to you, our audience. So taking a few moments to complete that is vital information that we always try to use to make sure we are providing you with the best experience possible. You will also see in the chat pod coming over the next few minutes, Tyler will be placing links to our social media outlet, LinkedIn, Facebook, and Twitter, as well as outlets to our email or our website, where you'll find all of our no-cost webinars, as well as success stories and research reports that we're putting out. You'll also see a link to our podcast coming up there as well. Again, thank you so much, Dr. Lurie, for your presentation today. Thank you, everyone, for joining us. We hope everyone has a great rest of your afternoon. And echoing as Dr. Lurie said, please stay safe out there.
Hello?
We're still here, Dr. Lurie. We're just
Okay.
closing things out. You're more than welcome to hop off the line whenever you're ready.
Can you hear me?